started. And I believe we can like to make it nice. So we can start with the next section probably. Where I shall skip the page 128, and hopefully everyone have read that. And it's kind of weird to start in the middle of our chapter. So we should, here we have like a clean new topic to start with, and that is application of temporal difference for control. And the first method we will consider here, or algorithm, would be Sarsa algorithm. And I believe we got to some very important ideas for reinforcement learning in general. So it's important for us to understand this clearly and have a good practice with this. So to start, like first, let's discuss what is the procedure we follow here, and it's very similar to what we have done before. We use temporal difference predictions for Q value estimation, and then we use generalized policy iteration to make to solve the control problem. So with Monte Carlo methods, we had a following like sequence of actions. So first we ran through all the episode, and after that we like iterate the episode in reverse and update our Q value estimates. But with temporal difference approach, oh, can you hear me?
Yep.
Okay, so something weird with Zoom. I got kicked out from the TWIML account, but that's fine, I guess. Okay, let's continue. Yeah, so with temporal difference approach, it's we update Q value as we progress through the episode. And here, the name Sarsa comes from the, basically from the information we use for this update. We need a state, an action, a reward, and a next state and action pair to do the update. And here it's in this formula. So we can take a look at this formula in detail. We have our previous estimate for this Q value for the state action pair, and we update this estimate with what can be considered a difference between our previous estimate and the new estimate we get after taking an action A at state A sub t and at state S sub t. So after taking that action, we observe a reward. Here it's denoted R t plus 1, and the expect like or estimated Q value here would be the sum of observed reward and the Q value for discounted Q value for the next state and action pair. And we update our current estimate with this difference multiplied by some alpha, which can be considered like a learning rate. And in such a way, after taking an action and observing the reward, and
voice is breaking up.
I'm breaking up. So the
And
connection.
Yeah, I'm not getting that.
No, you sound okay to me.
Yep.
Okay. So probably then it's on Mayank's side, right?
I think so.
Okay, in this case, let's continue and we'll see if it proceeds. Okay, so the backup diagram for Sarsa is this simple. So basically we have a state action pair here. We like do some action and then we observe a reward to get to the next state and then we decide on the next action. And after that, we can do an update for our Q function estimate. So that's basically it for Sarsa. And here is an algorithm written in like a concise form. So let's have a look at it to make sure that we understand it. So we have a bunch of episodes, and for each episode, we start with in some state S, and then we choose an action, and the choice of an action is driven by the current Q value estimate, and then we proceed in the episode, and at each time step we take an action A and observe the reward, and we get to the next state. And when we are at the next state, we again choose the next action by following our epsilon greedy approach derived from Q. And after that, we can update we can update our Q for S and A as given by the equation 6.6. And at this time, we can also update our policy if we want to have one. But basically, our policy is completely determined by the Q value, right? And after that, we assign the current state and the action to be S prime and A prime. So we like proceed one time step in the episode, and we go in circle, like we proceed further until we terminate. Okay, and let's consider this example here, which will give us an understanding how all these things work. So the problem here is simple. We have a grid world here, and this grid world is a windy grid world, so that at some locations, our action does not take us to the position we would expect, but it rather takes us to the basically our movement is also determined by the wind we have here. And here you can see that the values for a wind are specified in the beneath the grid. And this figure shows a strategy found by Sarsa algorithm. And basically, let's switch to the notebook, and we can play with it a bit. And yeah, probably will share everything here, and that would be more convenient for us. Let me switch to the notebook. Okay, so here I implemented this Sarsa algorithm, and basically what you can try to get the idea of environment dynamics, we can disable the wind, and in that case you can see that the agent deterministically goes towards the goal, which is here, and the basically Q or state value estimates are function is nice, smooth. You can see here it just deterministically we have high value as we get closer to the target state or terminal state, and we can add some slight wind, and in this case basically the agent finds some strategy that takes two downward steps, and then like affected by wind we go directly to the target state, right? So, and this is not like deterministic. You can see that in some cases we will find another strategy which also consists of two downward steps, and basically all the other actions go right. And if we rerun this a couple of times, sometimes it basically gets lost and doesn't find the good solution, but most of the time basically it finds this strategy which is optimal for this problem. Okay, and now we can enable our stronger wind as given in this example in the book. And again, sometimes it gets lost. Maybe if we run it for a longer period of time, it gets a better solution, but in general, that's what we get. So this is an optimal path we can get for this problem. Okay. Yeah. So back to the book. Do you have any questions regarding Sarsa algorithm or this particular example?
What was your code written in there? Is that R?
Excuse me?
What language was your code written in?
It's Julia.
Oh, Julia, right.
Yeah. I'm kind of learning Julia, and I've decided to code this stuff related to this book in Julia.
Right.
It's kind of fun exercise for me. Yeah, so let's consider these two other exercises we have. I haven't yet implemented this, but yeah, we can like briefly discuss it. So the first exercise proposed here is to resolve this grid world problem, assuming that we have possible diagonal moves. Yeah, and basically, obviously, if we can do diagonal moves, we can get to the target state faster, right? If you look here at the trajectory, we need to we kind of cannot go straight here. But if we would have an option to do the diagonal, like in this case, it would be southeast move. We would follow like a straight path here until we get to the wind that is like 2 in magnitude, and then we will probably it will take some path like going a bit downward and then going upward here when we have this stronger wind. And there is another question, is that can we do even better by including a 9th action that causes no movement at all? And yeah, I'm not sure if we can. Do you have any idea about that? I haven't yet think it through, but I will implement this in code and I will try out. Yeah, and the stochastic wind. So we need to, again, resolve this problem, but the wind will be stochastic. And yeah, so that would be another interesting exercise, and it will be quite straightforward to add this to the notebook, but haven't got time to do it yet. So, sorry. Okay, if we don't have any further question, we can move to the next algorithm we have here, and it's Q-learning. And the main difference here is that unlike Sarsa, which is on-policy algorithm, the Q-learn is off-policy algorithm. And by looking at this formula here, we can understand why it's off-policy algorithm. So while at Sarsa, we needed to select a greedy action here, and we used the Q value for state action pair with a greedy action selected as, for the next time step. Here we just select a the maximizing action here. So so in case of Sarsa, it was epsilon greedy action selection, but here we do just a greedy action selection. So we get the action that maximizes the Q value. And by doing that, we basically disentangle our learned strategy from the exploration strategy we use during the training, and we will get a good understanding how it works on the example here. So basically the algorithm is very similar, but the difference is that we update with the maximal Q value here. We use the maximum of Q function for state S prime to update our estimate, right? To compute the difference between the kind of new estimate for the Q value at S and A determined by the observed reward and the old estimate, right? And here we don't have this action. We don't need to select the next action, unlike in Sarsa, because we just need the action that maximizes our Q value for the S prime. Okay, and the difference between these two approaches is highlighted by this cliff walking example. Again, we have a grid world here, and for each action, like for each transition, we have a reward of -1, but for going falling from the cliff, we have a reward of -100. And you can see that there is a safe pass here, which goes through the like top part of the grid. And there is like an optimal path, which goes just near the cliff. And basically, what we can see here that the average, like the sum of the rewards during the episode for Sarsa is like higher than with Q-learning, and why is that? Because let's go again to the notebook here. The Sarsa algorithm. So here is the solution for the Sarsa algorithm. This blue line here shows the path which is found by the Sarsa algorithm to be the best. And you can see that at the location near the cliff, the algorithm wants to go upward. Oftentimes it wants to go up, because we have an epsilon greedy strategy, and like epsilon multiplied by 0.4 of the time, we will, when at the positions near the cliff, we will take downward action like randomly. And because that results in very negative reward, the Sarsa algorithm, like agent learning using Sarsa algorithm, prefers to go with a safe path. Basically, most of the time, it just goes by the longest but safest path. On the other hand, at Q-learning, we do not incorporate this high negative rewards observed when falling from the cliff into our Q-value estimate. We always take into account only the highest possible reward we can get here. And because of that, Q-learning learns this optimal path here. We do not take into account this negative 100 rewards when falling from the cliff. The Q value will be updated only with the highest the Q value for the next state, which is associated with the highest reward, basically, and that is always the like right action, and that is why it takes it prefers a risky but the more like faster path, right? So you can see that
we have I think so taken the negative 100 here too, but for this is an off policy approach, so that's why this I think if you
if we go to the implementation here, for example, when we so the update we have to our Q value is the difference for the previous estimate, right? So this is our old estimate, and this is a reward plus the discounted future reward, or future, how it's called, basically the Q value for the next state. And in this case, we take the maximum of the Q. So we basically when updating the Q value, we don't take into, so this like for the future reward, we wouldn't take into account the risk to fall from the cliff in the next state, right?
Mm-hmm.
So that what it means. Yeah, basically when we take the like here we take an random action, epsilon greedy action, and we can get the negative reward here. And yeah, sometimes so the you're right that the negative reward here is incorporated into Q value, but it's not basically not we don't take into account the risk to fall from the cliff in the next state, and that's why the like preferred future state for us is this one here for the Q learning algorithm. Yeah, you can find it here. So that is preferred when we hear this is preferred future state. And for the Q learning or for Sarsa algorithm, preferred future state would be here because it doesn't have a risk of falling down. And here you can see that we can compare like this average observed or the sum of the observed rewards for Q learning, which is red, and Sarsa, which is blue. And you can see that basically most of the time we here you see that the peak reward we can get during the episode when using like Q learning is higher. This is like you see the peak values for red. It's so it's higher, but we more often we basically get the -100 reward here. So we fall from the cliff at some point during the episode. And for the blue, which is learned by Sarsa, basically we are falling from the cliff much less often. So that should be some like unlucky coincidence that we fall from the cliff. But the peak reward we can get from the episode, it's lower because we are taking that safe path around the cliff. Okay, so that what basically determines the difference between these two curves, as shown here as well. All right, and okay, so let's discuss the questions here. So why Q learning is considered off-policy method? And yeah, basically that's because we are like because of this factor here, we take the we take the estimate for the future. Basically, this would be like a estimate of the future rewards, right? And we take it like the maximum value for it, not the value under current policy. So we just take a maximum, not a value under our current policy, or epsilon greedy in this example we use it. Do you agree with that, or any comments?
I would agree with that.
And Sarsa is on policy because we are basically taking that estimate for our current policy. Yeah, and let's discuss the next exercise. Suppose action selection is greedy. is Q-learning then exactly the same algorithm as Sarsa? Will they make exactly the same action selection and weight updates? So my understanding is that it is true that when the action selection is greedy, the Sarsa and Q-learning would be the same, right? Let's compare the formulas for the update. Here we have this maximum over all actions for the Q and state as t+1. And if the action selection is greedy, this component in Sarsa will become the same. So basically, the A prime will be maximum over Q given as for Q value for state S prime. And yeah, so this component will be exactly the same for Sarsa and Q-learning if the action selection is greedy. So would you agree with that?
Yes.
Okay, cool. Let's then proceed to the expected Sarsa. Basically, the expected Sarsa is kind of generalization of the two considered above approaches. And let's have a look at the update for expected Sarsa. In this case, we take this component to be the expectation under the policy pi of Q of ST+1, AT+1. And what that would be? That basically would be a sum over all possible actions of Q of ST+1 and A given an action under policy pi, right? Basically what we have here, we just have a weighted sum where the weights are probabilities of taking action A under current policy. And this weighting can be different. So depending on what the current policy is. And so the consequence of that is that algorithm moves deterministically, whereas Sarsa moves in expectation, right? Because like basically a Sarsa update would be randomly chosen action here, but here we have the expectation of Q under all possible actions. And that's why it's called expected Sarsa. And let's have a look at this plot here, which shows the asymptotic and interim learning curves for different settings. For Q-learning, Sarsa, and expected Sarsa. And you can see here that expected Sarsa gets the best performance both asymptotically and best interim performance. So it's kind of less dependent on alpha here. You can see that the asymptotic performance for expected Sarsa is the same, regardless of what value of alpha we choose between 0.1 and 1, right? While like for Sarsa, if we have high value for alpha, so we have strong updates, it basically the algorithm breaks at high values of alpha asymptotically. And yeah, and the Q-learning, it you can see that it kind of learns a bit slower compared to expected Sarsa and Sarsa. And also it's some of the rewards on the Q-learning is lower, but that's because it kind of disregards those risks. Yeah, so I forgot to mention that this plot is again for the this cliff walking problem we considered before. And yeah, I've tried expected Sarsa here for the cliff walking problem. And yeah, for this particular setting of hyperparameters I've used, it kind of took the intermediate path here. So in this case, we are taking into account the possibility of falling down from the cliff, but it has kind of less impact on the resulting policy we have compared to Sarsa. And basically, if we run it multiple times, if you see that it almost doesn't change, while there was a lot more randomness when using Sarsa here. Yeah, let me show it once again. So you see that for this number of episodes, I've chosen that basically their policy resulting from Sarsa, it changes from experiment to experiment, and the results from expected Sarsa looks to be much more robust. So, yeah, and in the book they do not show what would be the policy learned by expected Sarsa as they would give it, but I think that's something that very similar to what I have in that notebook. Okay, and here are the backup diagrams for Q-learning and expected Sarsa. So for Q-learning, you can see that as it denotes that we take the maximum over all actions. And for expected Sarsa, we take all the possible actions into account. Okay. Yeah, we can try for this to set alpha to be higher and see if it really works for Sarsa as they show in the book. I don't have this parameter here or something. Let me check quickly. Does it take alpha? Oh, it should be specified as n. Okay. Never mind. I will probably just check. Oh, all right. So yeah, you can see that we can safely train the agent using Sarsa algorithm with higher value for alpha. You can even use value of 1, and it has like the same result here. So this probably would speed up the convergence. Maybe we can decrease the number of episodes and see how it goes. Here you can see that even with 100 episodes, it converges. Yeah, but if we use a lower alpha, it's kind of, it cannot converge with 100 episode, but would converge with probably with 1000 episode, right? So that is nice about expected Sarsa, the fact that we can use a higher alpha and learn faster. Yeah, cool. Now we can go to the next concept if we don't have any questions here. Here we consider this problem of maximization bias, which we observed when using Q-learning. We take this maximizing action for estimate of the Q value for the next state, and that is why the learning algorithm is biased towards the towards randomly observed high rewards, and this is called maximization bias. And this maximization bias can be illustrated by the following example. So consider a simple, basically simple task. We have we start at state A here, and we have two possible actions, left and right. The right action results in 0 reward and leads to terminal state, and the left actions leads to the state B, from which we go. We can basically take multiple actions, which all result in the go into terminal state, and all the actions have random rewards, which are sampled from normal distribution with mean of negative 0.1 and with standard deviation of 1. And when we apply a Q-learning to this problem, at the very beginning, the Q-learning algorithm favors the left action here because it occasionally observes the positive rewards from this action, from some action here. So the Q value for certain actions from state B would be positive for a while the true expected value for all these actions is negative 0.1, right? And to eliminate this problem, there is a way called double Q learning. Yeah, let's cite this from the book. Suppose we divide the place into two sets and use them to learn two independent estimates. So we have Q sub 1 of A and Q sub 2 of A. And each estimate of the true, each of these is estimate of the true value Q of A for any any A, and then we can use one of the estimates to determine the maximizing action A prime, and the other estimate we use to provide the so we use another estimate to estimate the value of Q, right? And in this way, we will have an unbiased estimate in a sense that expected value of Q sub 2 of A prime will be equal to the Q of A prime, right? And the same is true for like a reversed situation, where if we use Q sub 2 to select the best action, and we will basically use Q sub 1 to select for the value, we will have again an unbiased estimate. And during learning, we can basically randomly select which Q sub 1 or Q sub 2 will be used for action selection, and which one will be used for value estimate. And this process is called double learning. And this double learning removes this bias towards the maximization bias we observed when doing regular Q learning on this stochastic problem, the problem with stochastic rewards. Okay, and yeah, and here you can see that the update is changed slightly in a sense that we select the action associated with the highest Q value using Q sub 1, but we use Q sub 2 to get the expected return for the state as t plus 1. And we can check this algorithm here. It's essentially the same as Q learning, but with this randomly selected Q sub 1 or Q sub 2 being updated, and another one being used for value estimate, right? So that is double Q learning, which allows us to avoid the maximization bias. And yeah, that's it about this problem. And do you have any question about it? So what would be expected? What would be update equations for double expected Sarsa and under epsilon greedy target policy? So let's think about it. We can basically, in a similar way, we can have two variants of Q sub 1 and Q sub 2, and we can select an action using, say, Q sub 1 with epsilon. We select an epsilon greedy action with accordance to Q sub 1, and then we use Q sub 2 to estimate the value. or vice versa. And yeah, I'm not sure if this would work the same way with Sarsa in terms of does it even have the maximization bias? Yeah, what do you think about it?
I think the maximization bias won't be a factor there, because if we break that up into now, since if we apply a max there in the Sarsa's equation, and now try to break that into two parts, two subparts, such that we have kind of a double Sarsa, like in double Q learning. So that will have a completely different impact, and I think so. Some folks have had this experimented, and they have this double expected Sarsa, or I think double Sarsa, in which they have tried this. There is also a research paper, I think so, there, which have experimented with the similar type of a Q learning values there. Yeah, I might share it in the chat after this session. But yeah, uh, in my viewpoint, I don't think so. We will have much of a difference there, unless we are trying to use a threshold like they have done in the the algorithm which we had just seen with the 0.5, and then they have tried to replace it with the Q1 and the Q2 part, and try to exchange it. There might be a similar way which might help in the Sarsas, but yeah, I'm a bit skeptical here too.
At the start of the section on maximization bias, he says that Sarsa has positive bias because of the fact that it is using epsilon greedy, is also using max. So you can see somewhere in there. Oh yeah, so was it the fourth line down there? Yeah, so it says Sarsa, the policy is often absolute and greedy.
Yeah, so we basically, every time we use this maximum operator, max operator, right, we have some kind of maximization bias, because like randomly high outcomes are getting like high weight and being selected more often under epsilon greedy, probably, as well as just as well as under Q learning, right? So
yeah,
so that makes sense. And in a similar way to Q learning, when we have these two versions of Q, right, we will have basically a different bias, like different randomly favored actions in these two Q variants of Q, right? And because those are different, we kind of eliminate the bias, right?
I think so, yeah.
So
but that distribution will be selected based on the parameter of the action that we have taken. So, okay, then the queue of the next state and the action that is selected based on that. Okay, I'm a bit, and then they try to remove the maximization bias by selecting greedy. Okay, uh, but here I think so. In the equation, when we try to input that, the how will we able to implement it? I mean, if I think about the proper threshold or the parameter that is required to implement it, that will be dynamically defined, or will we be a particular uh, uh, I don't know, manually selected, or uh,
So
from that
in
point of view? Yeah.
terms of implementation, I believe the difference here would would be follow. So here we have this step. Choose action A from S using epsilon greedy policy in Q1 plus Q2, right? But
Mhm,
for Sarsa, we will have a step when we select an epsilon greedy action
mhm,
for a state st plus 1 using only one of these, and then we use another one just to get the expected return estimate, right?
mm,
And
mm,
in this way, it's very similar to what we have do with Q-learning, but we will basically use another like two different variants of Q for selecting the future, like the next action here, and
mm,
and that will have the same effect that basically if we have if we have observed some unexpectedly high rewards for certain action, it will be selected here during this like first stage, right? But the expected return for that action will be taken from another Q variant of Q, which is the same in expectation, but hopefully it doesn't have this like randomly again much higher reward than the expected one, right?
Yep, that makes sense. Thanks.
Okay, cool. So let's then, and yeah, I think I will implement it after the end of the session, and we'll try it out. I will need to try these formulas and see how it works with different algorithms. The next section talks about an interesting idea that it's not always the case that we want to estimate the action value function or the value function or state value function, but sometimes we want to use something completely different and or not completely different, but slightly different and problem specific. And let's consider the tic-tac-toe example. If you remember, it was also considered in the very beginning of this book. And here we encounter an interesting concept of after states. So for tic-tac-toe example, we try to estimate a value not for a state or not for a state action pair, but for an after state. So after we taken certain action, we get to the state to a certain state deterministically, right? During tic-tac-toe. And here you can see that, say we have a state, this state and this state, and we have two actions here for these two states, and both of this action lead to the same after state. And because of that, we probably want to have the same value estimate or value function for the associated with this after state. We do not care if we come to this after state from state A or state B, but we only care that the resulting state is the same, right? And that is why we do associate the values with an after state rather than with state or as an action. So that is interesting, interesting new viewpoint to all this problem formulation, and we can argue that like in reinforcement learning, selecting a good problem formulation is kind of an art and should be specific to your problem, right? And if you remember the Jack's car rental problem from example 4.2, it can also be formulated with after states. And if you don't remember, let me remind it to you. So let's just maybe jump to the section. For in that problem, Jack has two locations where he gives cars for rent, and he needs to move the cars from one location to another overnight to make sure that he has available cars at both locations. And in chapter 4.2, we consider this as regularly we learned a value function, a state value function for this problem, but actually it probably would be better for us to learn an after state function, because we do not care like how did we end up having a certain amount of cars in location A and location B. We only care about how many cars we have in the morning at each location, because we want to have available cars at both, right? And so arguably this would speed up the learning, because we would be learning a value for the resulting state, not for the state at which we start before we take an action. So we would observe basically more more outcomes for each of the states in this way. So we will be able to associate more outcomes with certain after state than we could with a certain state. Okay, so that is what this chapter talks about. Yeah, in tic-tac-toe example, like we don't know what would be the next action of the opponent, but yeah, we do not care how did we get to this state. We only care what the kind of expected return for this state is, right? Yeah, so to summarize, the temporal difference methods are alternative to Monte Carlo method for solving the prediction problem, and the control problem is solved in a very similar way for both of these cases. So basically we use either temporal difference methods or Monte Carlo methods to estimate the state value function or action value function or after state value function. And then we use generalized policy iteration to update our policy accordingly to the value function estimate we have. And so this temporal difference methods considered in this chapter can be more precisely called one-step tabular model-free temporal difference method. And the temporal difference methods may be much more general than what we have considered in this chapter. And in the next chapter, we will take a look at the generalization of temporal difference method and like Monte Carlo method, which is called n-step bootstrapping, when we can basically use multiple like information from multiple steps into the future to update the value function for the current state. So basically that's it for this chapter, and we can continue the discussion. And yeah, feel free to point out anything I might have missed, or ask any question you want to bring up, any question you want to discuss.
I don't have any questions. That was good for me. Thanks, Arto. So yeah, it was good to get through that.
Yeah, sure. If there are no questions, I think we can finish this session. And yeah, I will finish up the notebooks and upload those. And I recommend you to play with the code, either using my notebooks, or there are a bunch of implementations in Python or in also in Julia. And yeah, just make sure to get some practice with it. And I had just one suggestion I wanted to discuss and see if anyone here would be interested in it. So I think that it would be nice to have like more practice with these algorithms now that we are getting to the really standard reinforcement learning algorithms. I think it would be nice to try those out in some kind of gym. So we could take any of the well-established reinforcement learning environments, for example, the OpenAI gym, or we can look at other options and try to implement the algorithms we are learning for other tasks and see how that perform, and probably that will allow us to better understand the like pros and cons of any algorithms, right? So what do you think about it?
Yeah, certainly. I think it's like the best way to learn them is to actually to implement them. I've played a bit with like OpenAI Gym, and yeah, like it has all that windy grid world and stuff. So yeah, it would be good to play with that and see it.
Yeah, I was wondering, like thinking about like applying it to multiple, maybe simple problems. You know, there are like a bunch of standard problems other than grid world, and I think this algorithm can be applied as well to this, like pole balancing and stuff like that, and other simple games. And it would be nice to see how all these algorithms perform in different environments. And maybe we will find the cases when some of the algorithms are not applicable, and that will probably give us like a better understanding of why such a great variety of algorithm exists, right?
Yep.
Okay, then thanks everyone for your attention, and see you next week.
Have we got a plan for next week? Will it be back to the normal time again, or?
Oh yeah, I think we can get back to normal time, and yeah, if anyone want to volunteer to lead the next week session, you're welcome. But I don't know. I think Mayank, you won't be able to lead the next session as well, right?
Yep, I have some things that I need to take care of. But I think Steve or you might take the next chapter too, with the ends bootstrapping.
Yeah. I don't mind doing next week's one, but then I'm on holiday after that for a couple of weeks. So like
nice.
I could do next week, but then yeah, I'll be out until the end of until the start of September then.
Yep. Just need for I will ping you and we can discuss the details.
Okay.
Yeah.
So okay with you, Ardo, or I don't mind if you want to do it, but I'm happy to take it if you don't mind.
Well, yeah, I could do next week, but I don't think I'm the best presenter. So
it's all right. Arto, it's fine. It was quite good today too.
Yeah, same here.
Yeah, all right. And yeah, and in that case, I can do the next week as well. And yeah, I'll probably have a bit more time to prepare for that, because this one was kind of, I wasn't certain until the last moment if I would be available today. But I can lead the next week as well. So however you choose, Steve.
I'm happy for you to do it. That's cool with me.
Okay, then deal. We will go through the next chapter next week, and see you then.
Okay, thanks.
See you guys.
Okay.
Thanks.
See you next week. Bye.
Bye, everyone.